So I'm gonna jump in into kind of the solution to this exercise, or how we might think about solving this problem. Um, so the first thing to know is that we can use I'm in the wrong thing. You can use this formula basically for calculating and estimating what the multiplier should be. So with only one variable changing, which is the number of them we own, which is kind of straightforward. As long as we have a multiplier and a base cost, we can figure out kind of everything else. So I'm going to jump into Excel and start making a couple of things here. Okay, so in this column, I'm going to put the number owned. In this cell, I'm going to put the calculated cost. Go. And then over here, I'm just going to create a variable for the multiplier. And I'm going to put a base cost. Actually, you know what? I'm going to just put the base cost here. I'll just call this cost. So the base cost was 15 for this. I'm just going to build these. Just try and make this a little bit more straightforward. Okay, so I'm going to initially set the multiplier to 2. And just to make this look a little bit neater, I'm going to just surround it with outside borders. So that it's clear that's a multiplier. 2 of these, I'm going to put a border underneath, or yeah, border around, that's fine. Perfect. Number owned and cost. So I can go 1, 2, 3, blah, blah, blah. Instead of doing that in Excel, I can just select these 2 cells and drag from this corner here down. And let's say we can get up to 26 of these owned. So that gives us our number owned. So now we're going to need to use our formula, which was, if we jump back to the slides, it was this. So they say cost equals base cost by multiplier to the power number owned. So we can now we can do this in Excel, and it's fairly straightforward. We are going to start off with our base cost. So we're going to say equals. This is our base cost. Okay, and if we put a $sign here, it means when we drag this formula into downwards into other cells, it's going to stick to that cell basically. So it's always going to reference this one cell. Then we are going to multiply that by power. And to do power, we just do our multiplier. And the multiplier, I just want to do the same thing, make sure that that is a kind of static reference to that. And our power is, our number is that, so that's our multiplier, and the power is the number owned. And we do want that to change, so power of 1, is that right? Let's see, cool. Okay, so that's our formula there. As you can see, with a doubling relationship, this number gets pretty huge pretty quickly. Okay, so we can tell 2 is not correct. And so we know it's 15. Sorry, and what did I say the next one is? I've got it here in the browser. Sorry, that's just uploading. 18. Okay, so if we can get somewhere towards 18, and let's just see what the next one is. 18, 20, 23, 27. So we're looking to get 18, 20, 23, 27. Okay, so that gives us some idea of what we're doing. There's a few ways we can go about working out how this would work. So we can basically look at doing the reverse of this, of the formula we're doing here. And that would be that we actually know the base cost and we would work it backwards, or we can kind of try and guess this. So right, if we go 1.5, Okay, if we go 1, obviously not 1, 1.25, that's still too big, 1.2. Okay, so we're getting fairly close. If we go 1.5, sorry, 1.15. Okay, we're getting pretty close there. And if we just take this formula and we round it up, oh sorry, I need to say, we can see if we have something pretty accurate. Cool. 827, so then we should be able to predict that the next one, once we have 6 of them owned, the cost will be 31. So let's go here. Or the cost to buy 6 of them is that right? Did I buy too many of them there? So we have 35. Yeah, 35 because we own 6. So to own 7 of them. So to own 8, it should cost us 40. Should be the next number we'll see here. Yeah, cool. Okay, so that predicts pretty accurately how that's going to work. Now, the interesting thing about this is that when I mentioned about like only using the one value basically, and a minimum number of values, God, it takes a while to get cookies when you're this early on. So grandma costs 100, 115. So what's interesting here is I'm gonna say 100, and this is where am I? This should be H1. So there's my multiplier to the power of, oh yeah, my number one should still be on the A column. Cool. So basically in Cookie Clicker, you could go through all the different like items that they have and the different starting costs of them, and you would find this formula would be predictive of all of them. Okay, so everything in Cookie Clicker is basically built to this formula. We can graph this as well if we want, and we can see that these basically follow a similar graph. So if we select these and we go, I think it's insert, and we can do a line, we can see the curve that follows, and we should see, if we type in cursor, cost, and grandma cost. I've spelled that very badly. And I can insert another graph for this. Okay, they basically, even though the scales are different, so this goes up to like 600 and this goes up to like 3500, we can see that the curve follows a similar shape, and that's because we're following the same exponential curve. If our multiplier here was like 1.2, you'd see that the curve gets more extreme. If it's like 2, it gets really extreme. If it's 3, which is what like the start of the pandemic was, you get like numbers that are pretty extreme. Okay, so that's basically what your multiplier is doing there, and that's the formula that lets you work out how to do this. You'll find a lot of games tend to use something in and around this region of like 1.15, especially these incremental games. It's like it's basically kind of a magic number for that genre. So to jump back into the lecture, so yeah, that's basically the way the curve looks. So we can graph like the number of owned follows a linear curve, and then the cost of each one grows exponentially, which means that like to get your first cursor is a lot less work than it is to get your 27th cursor. And here is, yeah, this is the Excel formula basically we can use. Okay, and it's just they round up, so sometimes it's a little bit hard to figure out the exact number. But yeah, they're just basically rounding up for it. If we want to do this in Unity, so if you want to have your enemies in Unity, like their health, let's say each time you kill an enemy, the next enemy gets stronger, you can have like a var for their health, and it would be equal to like the base health by mathf.pow, which is your power formula. The multiplier would be like your health multiplier, and I would be the number of enemies you've killed. So each enemy you kill would basically get exponentially harder depending on the multiplier you have. Okay, or like if it's resources, you might collect exponentially less resources as you move through an area collecting resources. Yeah, and these are basically what are called exponential curves, and they're very common in games. You'll see them used a lot because they're kind of predictable, they're understandable, and they give you like nice, interesting sort of interactions. You can flip, if you flip the last two parts of this formula, so you still keep a cost equals base cost by. If you multiply the number owned to the power of the multiplier, you get what's called a polynomial formula. They're used slightly less, and that is, I think, generally the curve goes like kind of a little bit more crazy, basically. And we can jump in here and just check that out, because all we need to do is swap. Let's say if our grandmas were polynomial, which sounds like we're saying something bad about grandmas. And hopefully no one has polynomial grandmas. Yeah, go. So the curve kind of goes this way. Right, I might need to go A3 for this. Yeah. So it's like, it's pretty much like almost a straight curve. It doesn't increase by as much. Let's say if we go for 2, you might start to see it looking slightly exponential and stuff like that. It's just it's a useful formula, but it is a little bit less nice to get a feeling the way you'd want it to. If you have a low multiplier, things increase by very little and it's very gradual, it's almost linear, and if you have a high multiplier, they just increase too quickly. So that's why we often tend not to see these that much, but just to know, if you flip those, you do end up with a curve that you can use as well. Yeah, so that's basically like thinking about those curves and those numbers and the sort of thing we'll be using. So then there's a few math principles and a few sort of probability concepts I just want to run through before we finish up today. And a couple of these are intuitive, and some people think them intuitively, and then others are like things that seem intuitive, but you really don't realize it until you actually think about it. So in terms of dice and luck, so there's like a question here, like, do dice increase randomness? Okay, so like one dice is, or one die is obviously random. It gives you a 1 in 6 chance of any possible outcome. Let's say if it's a standard dice, if it's a D100, it gives you a 1 in 100 chance. If you roll 2 dice, I want you to think about if you think that would be more or less random than rolling 1 dice. Yeah, so normally if you roll 2 dice, what you'll find is that the outcome, because you're rolling 2 together, you basically have you end up with like a bell curve sort of shape. So you end up with a larger range of numbers. So if you roll 2d6, you end up with numbers between 2 to 36. But 1 in 6 of those numbers is 7. So basically you're more likely to end up on a number 7 or near 7 than any other sort of number combination. So actually it might seem unintuitive that like adding more dice makes it less random, but the more dice you have, the more predictable it is where someone ends up in the game. The one thing is that does not, like if you've ever played Risk and you've like rolled 16 dice and assumed you have to surely have some of them come out well, then maybe sometimes this randomness just works against you too. But Risk is kind of a specific thing where individual dice have to beat other dice, so it's like you've got the individual randomness. It's kind of it's a set case of this sort of thing. So yeah, the more dice you have, the less random it is. Basically, the more predictable the outcome becomes. And these are what the what you'll see in terms of the probability distribution. So if you roll 1 dice, it's a 1 in 6 chance of any possible outcome. If you roll 2 dice, a number 7 is the most likely outcome. So most of your numbers will end up in the region from 5 to 9, with the others being outliers. If you roll 3 dice, most numbers end up between like 7 and 14, with a few numbers that are outliers. And if you roll 4 dice, most numbers are pretty much between 10 and 18 with a few outliers, even though that goes all the way from 4 to 24 there, basically. Okay, so you end up with like a tighter range of possible outcomes, basically. So if the movement in your game is based on rolling 1 dice, there's a chance a player will move 1 space, like 1 turn, and 6 spaces another turn, so it ends up being very random. If they roll 2 dice, it's much more likely that they end up moving 7 spaces per go, or close to 7. So you can kind of predict where people will end up. And if you ever played Settlers of Catan, that's why you move the robber on a 7, because it's a thing that happens quite commonly. It makes it an event that occurs regularly within the game. So then there's this idea of past, present, and future, and this goes beyond, let's say, how we think about probability and chance and possible outcomes. So I think as people, we often have this feeling that if we've been like unlucky before, like we'll keep being unlucky, or if we'll be lucky, if we've been lucky before, our lucky number will come up again, or something like that. Okay, so we have this sort of expectation that that numbers have a predictability to them. So like it's this thing of like, does past randomness affect future randomness? So if I flip a coin and it comes up heads 5 times in a row, what are the odds it comes up heads again? Okay, so it's actually like on that specific coin flip, it's 50-50. Do you know what I mean? That like it's still just as likely. The one thing you're having is that like all those 50-50s basically multiply together, so you would expect over time to have a tails. And it's the same thing of like which list of numbers are more likely to win the lotto. So is it like 1, 2, 3, 4, 5? Sorry, I just had to sneeze. Is it going to be 1, 2, 3, 4, 5, 6, or is it 6, 23, 42, 44, 15, 66? And the reality is that either one of those like numbers is just as likely as the other to come out, even though it doesn't feel like it, even though it feels like you would never possibly see 1, 2, 3, 4, 5, 6 come out in the lotto. That's how unlikely it is to win the lotto, basically, that like it is so rare for those numbers to come out in that order. And this is like if you do coin flips like across a number of trials, you'll basically see that statistically it basically averages out, that like as you do more coin flips, you basically end up with like kind of having heads then tails, basically is the most likely outcome. But sorry, I think they did 4 coin flips, sorry, and it's just a random trial, and let's say 4 heads, like so you flip a coin 4 times, that happens 9% of the time. Okay, and 4 tails happen like 6% of the time. So somewhere there around like 7-8% is what you'd expect of like random chance that you end up with the same number, even if it's a 50-50 chance. That like if someone said, okay, if you give me €100 a week, like I give you a 50% chance that like I'll give you 3 times that, or something like that. There's still a good chance that you lose your money there, basically. So just bear in mind that like even though these outcomes are less likely, they're still outcomes that happen. You even though you'd expect if you toss a coin 4 times, you get at least 1 heads. It's just as likely you have 4 tails. Okay, so regression towards the mean then is another thing that's kind of important to think about. Is kind of how past randomness can affect future randomness. So this is sorry, that's the wrong slides. Sorry, this is regression towards the mean, basically. So in a normal distribution, there is a mean, which is like the average, and generally in a normal distribution, things will start to regress towards the mean. And what this means that like if you play any games with like ranked matches or something like that, and you have a really good game, your performance. I'll try and change the cursor here. Your performance might end up being over here. You might end up like having, yeah. Oh, can you hear me? Oh, so basically, if you're doing like ranked matches or something like that in like an online competitive game, what you might find is you have a performance that ends up being towards this side of the curve, like a really good game. Similarly, you might have a couple of really bad games and you end up this side of the curve. What regression towards the mean is all about is that the more you play, basically, those good matches will be balanced out by other bad matches that you have towards this side, and you have a mean performance or an average performance that is here. What happens in ranked games is that this is like your player rating basically, and as your performance improves, if you end up having matches that are consistently this side of your average basically moves forward and your average performance is now rated off a different point, off a different standard basically. But then performances you have will be based against that. So if you then start having you like have a bit of a tilt and like you're losing a lot of matches, your rating might kind of drop down, and then you'll find yourself kind of matched to games at that level as well. Okay, so that's the regression towards the mean. It basically means that like one good performance doesn't doesn't mean that you're actually better at something. It just means that it might just be one good lucky performance. Um, so basically, the chances are over time you end up like averaging out at a more expected place. So let's say like you end up, let's say you normally get like 50% in college assignments, and you do one assignment and you get 90%, and you think, oh yeah, I'm great, I'm really good at college. But then all of a sudden, all your other assignments come in at like 40. That's you regressing back towards your mean or your average kind of standard. Okay, so that's kind of principle behind it there. That like one individual performance doesn't necessarily predict someone's capability. Rather, it's the average of performances or the average of outcomes tends to suggest that outcome will return towards the mean over time. It's like a professional or like a professional gambler or player who thinks like they're really lucky. Eventually, they're going to end up like losing just as much as they're winning, or even losing more, and coming back to a more expected performance. Cool. And so that is kind of the key aspects. Turn off the laser pointer. That is sort of key aspects of numbers and thinking about like some of the probability and some of the things that are useful in terms of curves and maths. So if there are any questions, let me know in the Discord is the best way.